my suspicion and evidence so far shows that probably a lot are not understanding the gravity of the situation. Sure, they understand the way their equipment goes down. They see it. They fight through it. But how much do they know that it's actually a power quality issue at their core? You know, I don't know. You have welding, or you have large robotics that are creating transients right next to something that is very sensitive. Well, that's a real
Interesting
trouble, right?
Welcome to Manufacturing Insiders. Today we are going to talk about a topic that is really one of the major hidden issues that manufacturers deal with. Something that affects their uptime, that affects the precision of the work that they're doing. And a lot of people aren't spending enough time thinking about it. Kevin is a PhD. He has a PhD in mechanical engineering. His undergrad is in electrical engineering. This guy has a long track record of making big waves in some highly technical fields. And he's developed some solutions to analyzing power quality and really optimizing the performance of your facility. So I think what he's going to share today is going to be very interesting. One quick note, if you are listening to this podcast and you have some interest in joining, you're president, vice president, CEO, a leader in the manufacturing space, go to manufacturinginsiders.com, fill out the form there. We'd love to have you on. And but welcome to Manufacturing Insiders, Kevin.
Yeah, thank you. Thank you for having me. Great. Yeah.
Yeah, so give us a little bit of the background. How did you get to where you are, kind of developing your own hardware and software solution in the energy space?
Mm-hmm. Yeah, I mean, there's the long story and the short story. I'll give the shortened version of the long story, I guess, is, I've always been about engineering, and renewable energy particularly. And my career started at Ford Motor Company, which I actually got some experience with manufacturing, launching new vehicles. But on the engineering side, got deeper into renewable energy systems, fuel cells, hybrid electric vehicles, just all sorts of energy systems. That led to my my PhD in mechanical engineering. Wanted to dig a little bit deeper into just energy and physics than electrical engineering purely does. And then came out of that, went back to University of Hawaii as a faculty member, pivoted at that point into electric grid, and this is like mid 2010s, and really in Hawaii now, which is where I'm based now, and University of Hawaii was where I was, is sort of the epicenter of challenges around integrating renewable energy on the grid. Being an islanded grid and with high renewable energy mandates, it's a really challenging problem, right? So got into that from the grid side, but then started to realize the limitations of the data that is available to do the things you need to do to manage the grid properly. And so at University of Hawaii, I had an opportunity with some students and some funding to start building some hardware that would measure and control and do things for projects. And that went into a patent, that went into an opportunity to spin things out under an incubator program from University of Hawaii. And then that's been my own company, bootstrapped for the last 3 years, and now exiting from that into a pre-seed round. So we developed our own hardware circuit board levels to really dig at this deeper layer of data that is there to analyze power quality issues, which again are a big problem. We can talk about that more, but that's a little longer than I wanted. But my journey into this whole thing.
Yeah, it's fascinating. Yeah, and they're all fields that are extremely interesting to me. I did do a 2.5 years. I didn't finish my mechanical engineering degree, but I went to Penn State for 2.5 years before joining the Marine Corps. So I have a little bit of a background in it. And then I ended up going and getting a master's in business and didn't get back into the mechanical engineering, but getting into the manufacturing space, working with manufacturers every day, I feel like that, that little bit of background has provided value. And I've always been fascinated with the field. Like, I feel like the electrical engineering plus the mechanical engineering has a lot of applications with things that I love to ponder, like using gravity for transportation. I don't know if you've ever gone down that rabbit hole before.
I mean, not the rabbit hole, but I've definitely done the pot drinks. Maybe not that particular one, but yeah, exactly. Yeah, maybe what you're heading at, I think you are, and it's what fascinating me is yeah, I'm a PhD, sure, but I am just fascinated with the real world, like grounded in the real world, and it's honestly why I didn't stick within academia. You know,
Yeah.
I'm not about publishing papers as much as I really should have been if I was academic track. I'm more about solving the final problems and building the things and doing the stuff that makes sense. And manufacturing is and transportation, like goes in the grid. They're all areas where like the rubber meets the road. It's the hard stuff. It's the practical stuff, and I think that is where I live and thrive. And so the system I built is, I mean, it's hardware, it's circuit boards, it's firmware, it's AI now we're integrating into the whole thing. It's the whole stack, which I just
Yeah.
love because it's all that for a purpose to solve a problem, which is a pressing problem, right? And
Yep.
yeah, so
How overlooked is this problem? Like if you were to
I
look at the manufacturing space, how few of them are thinking about this topic?
well, to be honest, we're still starting our outreach to really get out there to a larger degree to be able to assess that. But my suspicion and evidence so far shows that probably a lot are not understanding the gravity of the situation. Sure, they understand that when their equipment goes down, they see it, they fight through it. But how much do they know that it's actually a power quality issue at their core? It could have been, failing some component that you just thought, oh, that just failed. Well, maybe it failed because of power.
Hmm.
You don't really know. The data doesn't exist. And it's been said that 7 out of 10 equipment failures of unknown cause, that's kind of a mouthful, are due to power quality. So when your equipment falls down, it goes down. A lot of times, sometimes it's clear, hey, this part failed, and you replace it and it's clear. There's other cases where, it fails and you don't quite know. You turn it back on or you whatever you need to do, but it's kind of an unknown cause, really. And it's
Hmm.
that 70% of those times are power quality. So that's a pretty big number. And then, if you put it back to EPRI saying that, oh, well, roughly, it's a ballpark thing, but around $200 billion of cost in power quality issues for U.S. industry. So, I mean, that's just a tremendous number that, you hear about like cyber attacks, right? Like they make the headlines. It seems like it's an attack. It's like, hey, you can put a finger on it, or
Right.
maybe not. I mean, it's come from the country, maybe, but like, it really has this sort of, feel to it. Power quality is kind of this ambiguous concept. Where did it come from? But 200 billion is twice the cost of cyber attacks, right?
Wow.
And I think it is that ambiguous sense, and I struggle with that. Now as trying to scale this out and get out the message and gather investors and things like that. You know, electricity is already an abstract concept, right? When have you ever met an electron? It's when you got shocked maybe once or a couple times in your life. Like, you don't see an electron, you see its effects, sure, but like, and now we're talking about AC power, waveform, okay, AC, 60 hertz, fine. Now you talk about real and reactive power, active and reactive power. You're talking about harmonics. You're talking about distortions. You're talking about sags and swells, and pretty soon people's eyes just glaze over. They're like, "This is just, it's abstract of the abstract," and you forget that even as abstract that is, it still costs cold hard dollars.
Yeah.
And I think that connection is kind of lost in the market so far, being that it's not traceable largely, and it also is this abstract concept is just. But as the U.S. emphasizes, manufacturing more, as especially towards advanced manufacturing, where power quality is even more important.
Hmm.
As the grid is even more stressed now, data centers are taking up more and more power on the grid. Sorry.
Yep.
Um, data centers are taking more power on the grid, at least 3 to 4% over the next years here. Um, and then, with renewable energy coming online, which I'm a proponent of renewable energy, I'm not going to hide that, but like it does come with challenges, harmonics and variability and all. So all this convergence is happening. 25% growth on the grid in consumption in the next decade, as well as increased need for power quality, more variability in harmonics due to renewables and EV charging and all these other things. And the electric utilities are just they're struggling. I mean, not they're in a hard spot to meet all that need. And then, is it when you have a manufacturing facility or anything, a hospital or whatever facility you have that cares about power quality, you might see this equipment flicker, act a little funny, and you're not quite sure why. You have an option basically. You can fight through it. You can hire a pretty high paid consultancy firm to come in and equip your equipment, and they'll take a survey for a couple months and report back on you, like big money. Or you start hassling with the utility and you say, hey, utility, we're seeing some issues here. And, if you're a big enough customer, I'm sure they'd take you seriously. But if possibly 80% of the time is what they say, the facility, the issues start within the facility. So the utility can't really solve it for you. I mean, they might come out and put a meter on the outside of your building, but inside your building is your issue. They're not going to help you with that. So it's just a real disconnect. And I'm just reaching out there with our equipment and trying to make more and more contacts within the manufacturing space, because I see it as the real pain point, right? Like in entrepreneurship, they always teach you, start with the pain point where people really are having trouble,
right.
It's opportunity to help. And it seems like to me, all this is converging on advanced manufacturing and possibly medical technology, those areas.
Right. Yeah. And I mean, when you look at that $200 billion number, I don't know exactly what that study measured or how they came up with that number, but there's probably, I would assume it was hard costs like machines breaking or, but then you have situations where, you're doing precision machining within, a 1 mil tolerance, and you get a power surge. And it may not be a massive power surge, but how does that influence the precision of that machining job?
It's hard to say, right? I mean, yeah, it's sure that machine has sophisticated control system and tolerances within it, and it's generally built to be somewhat robust to these sags and swells, but only to a limited extent, right? Like if the swell or the sag is too bold, then you're gonna have trouble. And there's particular specs, like within semiconductor manufacturing, there's a spec called SEMI F47. It basically measures voltage sag tolerance. Like if the voltage sags down to whatever degree, how long can it do that where your equipment should still tolerate it versus. Right. So basically what happens is a lot of these cases, there's a little bit of a finger pointing game at some point, because the equipment failed, or the equipment did not operate as intended. Now, was it the equipment manufacturer's fault, or whether it's the utility's fault, or even the utility's fault? But, probably has to be solved either way. But when it comes down to attributing the cost of that, then it really matters where it came from, right? And so there's this sort of, challenge, not just to fix it, but actually to figure out who's responsible for it too, right?
Right. Yeah, and it almost seems, I'm not going to pretend to be, a super expert on anything like this, but it seems to me that voltage sags would be a lot more difficult of a problem to fix than voltage spikes, because you can filter something down, but how do you add to it? You'd almost have to use some sort of capacitance or something.
You're right. You had a good point there. Sure, you can use a surge protector to knock off the peaks. To be said, power surge protectors are not perfect. Some passes through as well as they wear out over time. If they trim too many peaks, they eventually need to be replaced. But so there's that. The sags, you're right. You need an allocation of more power, more energy into the system, and a capacitor can do some of that. But a capacitor is a passive device. It does, in itself at least. It does not. It filters and it smooths that out, but it doesn't fix it, right? So how much fixing versus, is necessary, and is a straight up capacitor going to work? Probably not, honestly, because capacitor. First of all, capacitors. If you put a capacitor on an AC power line, you're applying reactive power. You're not applying, which might help your power situation if you're in a deficit of reactive power, but like you're not going to really solve an active dip in power unless you have some power electronics associated with that capacitor. At that point, you probably need an actual battery associated with it too. There's lots of things you could do, but you're right. It's not cheap or easy, and each of those things also has repercussions. Like you might be putting in a fix, but the fix could also cause trouble if it's not integrated right.
Right.
A lot of these facilities, like let's say data centers, in DoD facilities, hospitals, largely work upon an uninterruptible power supply, right? In that case, what they usually do is they have a battery system that can, support the whole facility for at least 10 to 20 seconds or more, enough to get a diesel genset online, right?
Yeah.
And of course, during that transition, there's, little hiccups in the power, which can also cause their trouble. And it's coming out more and more that even if you have those things, you might be still prone to outages because there's a significant amount of human error in these things. Like if you misconfigure your generator, some setting, some transition point, some transient is not quite right, it didn't trigger to turn on quite right, you could still have a failure, right? So it's not bulletproof either. Of course, it's very costly too to maintain. So yeah, it's coming out more and more that even these microgrids, I won't go into it because I won't reach anything here, but like these microgrids, are a good concept of resiliency, right? That they can operate offline. But if they're not developed right, or there's particular, things going on, there can be power quality issues within that microgrid that actually blow out inverters or blow out equipment that's supposed to be creating that microgrid. So it's a gnarly kind of issue that at the surface you don't really think about much until you dig in. You're like, wow, this is a big problem and a lot of details, and it's not an easy solution either.
Right. Yeah. But really, the first step is seeing the problems, is understanding where the power quality issues are and measuring them.
Right. And so that's where we come at it. Like, sure, you would love to be controlling it. We're working towards controlling things, but first you got to understand your problem before you can solve it. Problem is, the existing, power quality meters, they are, in my judgment, of course I'm biased, but my judgment, they are not up to the task, right? They're not up to the modern standards of what we expect as far as data and processing power to solve this issue. And so what you have is power quality meters that take snapshots. They take little snapshots of, maybe up to 10 seconds of high-speed data triggered by things like voltage and frequency or some particular gross violations. And those are useful events. But what about the events that did not trigger that? They were significant enough, but not quite enough. Or there are a couple of fairly significant factors that just didn't all add up to a trigger point. There's a lot of data there, a lot of insight that gets lost. And they also don't, once that event's lost, it's lost. Like you can't go back a week ago and say, well, what happened at that moment? Yeah. And to me, in my mind, if it's a $200 billion problem, like that's unacceptable. Like
right.
Doing. And so, now with the modern chips and memory and communications and things, it's all possible. And what we've built, I don't want to dwell on that, but like what we've built is the ability to do continuous waveform monitoring for weeks at a time. So literally with no dropouts at all, we're measuring 224,000 points per second, and we're logging all that data. We're now building the AI and the processing on top of that to really come up with sophisticated ways to analyze it. But the point is, if your equipment failed and you didn't quite realize it because it was kind of in the nuance, you didn't know, you backtracked and you say, hey, my yield was, we had a bunch of trash product this particular hour or something, what happened? Our specs were out, what happened? And you don't realize it till days or even a week later. Well, we can index right back to that same point and say, oh yeah, we can correlate something there. There was a sag, there was a swell, there was this. Okay, so you have something going on here. Then we can really put further analysis in place, which leads to eventually control measures, which might be, in this case, us recommending that you get a particular surge protector or a particular extra capacitor or whatever it might be. But the point is, you need that data to be able to know what we need, right?
Right. Yeah, and it's amazing to think about the possibilities when it comes to actually measuring very specific data points of energy usage throughout your facility, because not only does it allow you to troubleshoot and get a surge protector where it's needed and things like that, but like we've talked about before, a lot of repercussions when it comes to saving a lot of money off your electric bill too, analyzing your peak usage and things of that nature. So it definitely makes sense that this is data that manufacturers need to be gathering.
Right.
So when it comes to implementation, I know, like you said, you're kind of in that seed funding phase right now. How long do you expect it to be before there's a solution that you can bring to market and start using?
Yeah, well, we're already in a beta program phase where we have hardware that can be deployed.
Okay.
We're working through the certification process so we can scale this, right? But we can produce these, we can put them out, deploy them with people who are interested, and get the data. It's a more manual process than we ultimately would like to be, a more automated in our data analysis and all these other things. But we have the capability to log your data, to measure current and voltage for these weeks at a time. If you have a particular campaign or issue, I'd be thrilled to talk to anybody that's on this podcast to have a real case study to bring this out there.
Yep.
And raise the floor of awareness, right?
Yep.
Because, I expected my first round of, deployments, and I have deployed, but we want to increase that. The first round will largely be the people that already see a problem. They already kind of know something's up, and suspicious of it. So let's go and let's solve it, but then raise the floor of awareness to where people that maybe don't even know they quite have a problem, then we can put these out there more fully and capture, I think, a sea of issues that are out there that are just swimming just below the surface, that are, causing degradation of equipment. Maybe your equipment lasts 8 years, then 10 years, that's significant, right? You just don't realize it.
Right.
And so there's a lot of things out there that I think are for the taking, but unfortunately I got to get out there with more and more points of measurement to get the data to prove the thing. And so I'm in this sort of chicken and egg problem of, investors, obviously they want to see, deployments, and we've solved a $1 million problem like right here. Well, we're on the track to do that, but have we actually solved that yet? No, because we got to get out there and we got to, and we're not certified yet, which costs money. So we're really looking for the early champions, not obviously just investors, but early champions of customers who want to have a problem. And I'm thrilled to work with anybody like that, right? I want to dig in and do the actual stuff, right?
Yeah, and that is the more challenging. There is a segment of the market that already understands that they have a transient voltage problem or whatever it might be, but then you have the other side of the market that maybe they just aren't aware of how long their machinery should even last, and if it's going under that, or if they're having a switch that's burning out on a fairly regular basis, whatever it might be. And I just wonder how you give people a checklist of things. If you're seeing this, this, and this, there's a pretty good chance you have a power quality issue.
Yeah. I mean, I could rattle off those things off the top of my head, but that's a really good point of something that I could put out there, almost a white paper or something that would kind of be your run through, go to, overview description as well as a checklist. That's a really good idea.
Yeah, that could be a great marketing piece.
Yeah, but because again, it's so complicated that to do that initial assessment, you shouldn't have to be a power quality expert. Just to be able to do a walkthrough, and there's particular symptoms that might, not the smoking gun, but might indicate things going on. Right.
Right. Yep. So you said that this kind of started as a research project inside of the university, right?
Yes, in a different market, a different situation. What I was at the time, and this is still on our roadmap to do, it was around that renewable energy integration. So addressing broadly the problem that in Hawaii and other places where there's a ton of rooftop PV, right, and the utility is really struggling with managing that, right? And what
Mm-hmm.
does that mean actually? That means that the power that's flowing reverse direction from the house out to the grid rather than from the grid to the house is at midday twice as much as what normally flow in the forward direction. So utilities like tunes their transformers in such a way to manage this sort of downward slope of voltage from the outward in. And now when you're flowing the opposite direction, you got twice the gradient in the other direction. And it makes a real mess, right? And
Yeah.
so literally that means fewer rooftop PV systems posted, things like that, or just limits. And that was from the renewable energy. It's like, we got to really fill up our rooftops with more PV. I want to see more of this. And that's, so I love that. But is that a pressing pain point? Unfortunately, no. And so I realized that that was not a good first entry point to measure, in this case, transformers, which are kind of the throttle point there. We can measure those very specifically, and that's what we did at University of Hawaii. But now pivoting and taking technology much further, but doing it in the what's called the behind the grid, in the facility space.
Right.
And as an entry point, utilities are particularly difficult to start working with because the sequence of events and getting spooled up with them as a customer is just a pretty big lift, right?
Yeah. So when you look at companies that would be great candidates for beta testing, kind of early adopters, is there kind of like a subsegment of the manufacturing space or a company size or the type of process that they're doing that is like prime for the picking that you think would make a really good case study?
Yeah, I mean, I have my suspicions. I want to talk to more to sort this out, but what I believe is generally higher precision means more stringent power quality.
Right.
Like you
Yep.
said, if you're trying to do due to 1 mil tolerances and a voltage surge or sag happens, you could think that control system might struggle to keep its tolerances. That makes sense. Also, things that are highly imaging oriented, like
Okay.
distortions and things like that, um, which also generally correlates, I think, to higher precision. Medical imagery is also, I know that's not manufacturing, but it's also an area. Um, Anything that is, facilities that have sort of a co-location of high power equipment and precision. Let's say, I don't know, you have welding or you have large robotics that are creating transients right next to something that is very sensitive. Well, that's a real
Interesting.
trouble, right? That's where you're going to create a situation within your system. And, there's particular mitigations that become, sure, you need an electrician to sort this out and to implement it, but things can be recircuitized, like moved over, sorted out so they're a little bit more isolated, even though they're, close next to each other. Physically doesn't mean they have to be so close electrically. So things like that, it's that high, even sometimes within a piece of equipment itself, you might see high power and high precision, right? And I won't go into particular types of equipment, but anything it's imaging oriented, and again, robotics or things like that, heavy machinery that's, because you got to realize that when a motor spools up, if it's a controlled motor under robot or wherever else, when it spools up, it's taking some interest current, right? And when it unloads, it could be, outlaying some regenerative power onto the grid. A lot of these are under variable frequency drives, which is also a culprit. A lot of heavy power machinery in industrial space is VFD oriented, HVACs, things like that. The VFD itself, what it's doing is it's a variable frequency drive, right? So the grid itself, and you're probably on a 3-phase power system if you're a manufacturer, has a particular 60 hertz signal, right? So naturally, you can make a motor that runs some multiple of 60, rotations per second, right? and that makes sense. Well, you don't know, you want things to be variable. You don't always want a fixed frequency, so that variable frequency drive allows you to decouple the grid from the frequency of the grid from the frequency of your rotation, right?
Mm-hmm.
So basically what it does internally, it takes that AC power, turns it essentially into DC in the middle, and then creates AC again on the other side. But it can create the AC at whatever frequency it wants. How does it do that? It does that by a bunch of transistors and logic and embedded controllers that switch those transistors at very high frequency, tens of kilohertz kind of frequency, and chop that frequency back up to create a simulated sine wave. AC is supposed to be a perfect sine wave,
right,
mathematically, but it never is. And in the case of the power electronics, it's creating it digitally, so there's noise there, right? Mm-hmm. There's harmonics, there's things that happen, and those harmonics are also stuff that creates trouble. Harmonics now, if you have harmonics are anything that's not the 60. So they typically think about multiples. Like the second harmonics is 120, and the third is 180, and like on up, right, to high frequencies. But any of those harmonics that are not 60 largely create power that is wasted because it goes into machinery that really can't tolerate that energy, and it doesn't go into work or rotation or whatever that machinery is supposed to do. And so it literally is wasted. And so it can be heating, lost energy. It also can be bad behavior, that equipment, things like that are, and even equipment that has just switching events, if you have a heating element or a heating system in this space, obviously it's trying to switch on and off to regulated temperature, sure. But when does it switch on and off? It typically switches on and off at the zero crossings, like at the point when that sine wave or that voltage is close to zero, because that's easier on the power electronics to do so. So you have a lot of chopping in and out of things, at this level of 60 hertz or something of that order. And so that can be transient. It's all, it's such a wide range that is why largely it's been the domain of power quality experts to solve this stuff. Right. The other one, I don't want to bore you, but is around, there's unbalance. There's are all three phases equal? There's also an issue with anything that could have a ground leakage associated, right? Anything that's wet or has old insulation or things like that are not just a power quality issue for the sake of keeping equipment up, but actually human safety too, right? Mm-hmm. So all this is, in that realm.
Yeah, there's a lot there. So what does it take to physically measure all this? How many, if you were to go into a facility, are you, putting this on the panel, where, on the service where it comes into the building, or do you need to have sensors on every piece of machinery? Like what's the setup look like?
Well, you kind of need to do a little bit of review and audit, a discussion of what's up. I would probably want to at least do a video walkthrough, if not a physical walkthrough, to see or at least see a floor plan, electrical single line diagram, to kind of, because there's so many points you could measure. You got to kind of understand where's the issue emanating from, where you think it is, what's the neighboring equipment. So I would want to typically deploy, depending, 4 to 8 units across the facility, maybe to have a little bit of baseline, like, hey, the signals are stronger here, so we have some information that looks like it's emanating from here, that kind of thing. So I'm a little bit more interested in the nuance there than just the facility level, like at your entrance panel, although we can do that. We may want to do that as part of it, but also giving a little bit more granular data of going to particular equipment. Now, it's probably, so there's two aspects of the measurement. One is voltage, one is current, right? And the current, you're snapping a current transducer around the wire, so you're going to need access into the panel to get it, right? Where do you get access to that? You got to be either in the equipment itself. You might have a power distribution panel or back panel of the equipment that we can get into and put that in, because a lot of times there's instrumentation wiring you can put it back of the equipment itself, or you go upstream to the circuit panel itself. But either way, you need that access to the actual wires, because when the wire is going, maybe it's overhead, bundles of wire, typically that would be bundled together. Like the 3 phases plus ground are all in one,
Right.
cable
Yep.
together, and you got to clamp around the single wires. So you can't really do it there. You need to be in one of these endpoint panels. And then naturally you're going to want to measure voltage at the same point, right? What do you need to measure voltage? You need actual physical contact to the conductors, right?
Mm-hmm.
If you're in a main panel, and you might in some cases have a spare breaker that's just unused or lightly used, right? We could easily go on that, so you're not even putting a new breaker. If not, then we put in a new breaker, which is really lightweight, as low as current as we can get, because we're just measuring, right? But we want to, if we can, put it on a circuit breaker that we could then flip off and make it easier to remove the thing or switch it out or whatever we want. So we do that. Of course, there's electrician involved. We want to do this right, and can be done with the right electrician with while your facility's hot, or we try to schedule it during a downtime, depending, right? But ultimately, you get this device. I'm sorry, I don't have it in hand, but the sensor itself, which actually can fit inside that panel, and I think that would be the preferred method. And it comes out with a plastic fiber optic cable, and that's really all I need. And I take that out to a computer that logs that data, allows their process to happen. So back to your question, like where does it go? I would probably rather have it at the equipment, because that's the point of truth for the voltage, right?
Right.
But you go upstream, you can measure more things at once. So it's kind of a judgment call. Unfortunately, no strict rule on it, right?
Right. Yep. And so then you have kind of a user interface then on the computer that you can, it has that whole recording, and you can go back to specific times and visually see what it.
Yeah. Right. So we have, like, at this point, a plotting interface, which is nice, but not ultimately what we want to put in front of end customers. We're right now in the very midst of developing a really nice user experience, which is geared towards facility managers. We don't want to bore, or overload facility managers with too much detail, like of harmonic plots and things like this. We want to have them know, hey, you have an issue here, or here's somewhere to look,
yeah,
whatever else, and even have an interface to say, if you want more investigation, generate a report on this, and you can give that to somebody else, or give that back to us to give a further investigation. So this is, we're pivoting from a sort of a traditional plotting, you got to be an expert kind of interface, to a more usable interface that is actually AI driven, that you can ask AI to say, hey, last Tuesday, can you pull that up? What happened here? What's the likely issues? And even before you pull it up, it's right off the bat when you log in, it's saying, hey, last Tuesday there might have been this thing that seemed strange here. Here's a plot of it if you want to look at it more. Kind of,
right.
We're really trying to make it easy, so that you don't have to be a power quality expert yourself, or don't have to hire one. You may hire one later when you finally want to, like, put a choke on this line, or put a capacitor here or there. Like, sure, you're eventually going to need a true expert, but can we push this a little further to get you more information easier, to solve more problems more quickly, right?
Right. Yeah, and it would be super cool, like, if it could give you some conclusions too. Like, if you're, kind of have a color coded, green, yellow, red. So your red are your critical issues, your yellow are your severe to moderate, and then, your green, you're good to go. If you have a point in the system that's in that critical area, that AI knows what machinery is there, and it can say, you're at risk of, shortening the lifespan of your machinery. And, just having that kind of deep knowledge of the assets that they have and what the impact of these power issues are.
Right. I mean, it's the sky's the limit on this stuff. It's so crazy, actually. Like, because, everybody sees what AI is doing, but they see it largely from the large language model, like ChatGPT and Claude and, all those normal names. What's happening behind the system at the edge? Well, there's a lot of companies that are building wrappers around the large language model. Okay, well,
right.
For you can be an agent to do your bookings, or like whatever it is, right? That's largely on top. What we're doing is downwards. We're going further into the physical system And to do that well, we're logging like 50 gigabytes per day per device. I mean, right now we're not heavily into compression. We can go further, but 50 gigabytes per day per device. I blow through a 1 terabyte SD card in 2 weeks, and so we tremendous amount of data. There's no way we're going to ship that up to Anthropic. Like, forget about it. Like the cost model, like, I mean, I would be bankrupt in a second, right? So we got to do a lot locally. And so there's a lot of, I won't geek out on it, but there's a lot of sophisticated stuff that's going on that you can do a lot of pre-processing. This is actually AI itself. It's an AI, model that's local, but it's much trimmed down, much easier manageable than what's up on Anthropic. You package that, you analyze it, you create the analysis package, if you will, and you ship that package itself up to Anthropic, and you say, hey, with all the global information it has around everything else, then it can get a better contextual final answer to you. But we do a lot locally because we locally have access to all that tremendous amount of data. So we can internally query, internally create plots that you are interesting or useful, and direct a lot just, directly with the user there.
Right. Yep. Yeah, it's fascinating. Yeah, and I have to admit, before I started this podcast, I was not aware of how big of an issue power quality and power monitoring and all of that is. I mean, but it's huge because it's not only a matter of you can save money on your electric bill in the tune of hundreds of thousands of dollars in some cases, but the cost, the upstream cost of, equipment failure, downtime, loss of precision, all that sort of stuff. So it's a big deal.
Yeah, I like to think about it like a value stack, right? At the pain point, acute level is what we're trying to like minimize downtime. Like when you do go down, maybe you get downtime be half of what it would be because you have the knowledge to turn it back on more quickly. Fine. Also, the risk that you're carrying if you turn it on, you don't quite know the root cause, and you could easily have a failure again in a week. Well, we want to do that, right? We also want to do things like reducing, wasted energy due to harmonics or things like that. There's also, like you said, peak shaving, demand charge reduction that you could say, hey, you're going past this limit here. If you shift your usage here, you could save this amount of money. Reactive power is another one. Largely utilities bill reactive power separately. That's another hit you can address. And so there's the whole like layers of value here, but all, like we said in the beginning, it all gets down to measurement, right? And it actually is that power quality has the highest challenges around measurement, like higher bandwidth, higher data, like all that, which is what we're solving. But it means that if we solve that, we can also do these other things really well too.
Yep. Yeah, pretty awesome. Well, I'm excited for you. And so I always ask this question towards the end of the podcast. And the question is are there any resources, relationships that you're looking to build, any problems that you're facing right now that if somebody's listening, they could approach you? I think you mentioned the one would be you'd love to talk to people that are interested in getting more data on their power quality. Linking up with you could help them install a system, start to measure some things.
Yeah, absolutely. So that's one level. I mean, that's would be thrilling. I would love that. I realize that not everybody is going to be ready to jump into that level. So I'd be happy to just have an interview, talk about this thing as we're shaping things like the dashboard. Like, what would you want this thing to look like? What questions would you want it to answer? Like, we're in the very midst of that. If you want to help, shape what that's going to look like in your own favor, like I'd be happy to talk to you.
Yeah.
Also even just literally having a discussion to honestly, I mean, self-centered, but like to support, to even vouch for this, to say that this is a problem that you're being concerned about. You had this story of, if you can even share a story that I can take to investors literally, like, and say, hey, not a sale yet, not anything, but I'm discussing this and I've heard directly from this customer who's willing to disclose that they have this problem. Like that goes so far in really raising my profile with ultimately investors, because this is the cost out there. So, yeah.
Okay. Yeah. Well, we'll make sure that we, put some methods of connecting with you in the bio of the video.
Sure.
But then if anybody listening wanted to have an introduction to Kevin or wants to learn more about power quality issues, you can just go to Manufacturing Insiders and fill out the form there, manufacturinginsiders.com, and we'll get you set up. But awesome product, awesome solution you're putting together here. You're a smart guy. I'm confident that you're going to be able to bring it to the marketplace. And let me know if you need anything from me as well. I've spent a lot of years marketing these types of solutions and kind of understand how to get them in front of the right people. So,
yeah, absolutely.
But thanks for joining today, Kevin. Great to have you.
It was a lot of fun. Thank you. Appreciate it.
You're welcome.
Happy to talk to anybody who wants to reach out.